So let's say I have a clock like this, which is having time period of t and frequency f. Okay, this is my time period t, so its frequency is f, let's say, and I want to get a half of this frequency. So what I need to do, I have to increase my time period to 2 times. So this is my second clock, clock 2. This is my main clock. The clock 2 is a having frequency of half of the main clock. Okay. So how to get this? One way is to get this is you just sense the positive edges of each of the main clock, and at every positive edge you just flip the data of this clock 2, right? So how to write this? You can write like this: always at the rate of positive edge of main clock, which is CLK. Initially you will take clock 2 is equals to 1 tick binary 0, and always at the rate of positive edge of clock you just flip the clock 2 to its clock 2 bar. So initially it is 0, now at the positive edge it is flipping to 1, and again at the second positive edge it is flipping from 1 to 0. By this way you can get a clock of f by 2 frequency, right? This is one way. The other way is you can do by using directly mapping the clock to at every by using a counter method, right? You can count how many positive edges that it is appearing. Let's say I want to create a clock of f by 4 frequency. Okay, so in this case what is happening, you have to count for 4 clock positive edges. So the f by 4 frequency will look like this, right? Because it is taking 4 time periods: 1 2 3 4, 1 2 3 4. It should take up to here, right? So it is taking 1 2, this is 2t, plus this is again 2t. So the total time period is t is equals to 4t. So the frequency is f by 4. So in this case what you need to do, you have to count for positive edges. How many positive edges are passing inside this? 2 positive edges, right? So you take a variable called count. Initially count is equals to 0, and then always at the rate of pause edge clock you just start counting whether the count is equals to 2 or not. You check. If the count is equals to 2, then assign the count is equals to 0, because we want to start the counting process again from 0. And my clock, let's say this is clock 4, which is my f by 4 clock. My clock 4 should be flipping of clock 4, right? If this is not true, then else start counting. Count is equals to count plus 1. By this, you can get any clock frequency by changing the variable of the count. If you are counting for 2 clock pulses, then it is a f by 4 signal. If you are counting for 4 clock pulses, then it will be a f by 8 signal. So we will see that once we do the practical. Okay, you can use both positive edge and negative edge same in one always block like this. Always at the rate pause edge clock, comma, neg edge clock. So what does this do? It will do the operation both at positive edge and negative edge, and you can use like this always at the rate clock. What does it do? It will do the operations inside the always block whenever there is a change inside the clock, or even you can use always at the rate asterisk. What does this do? Whenever there is a variable changing inside the always block, then it will be added to the sensitivity list, and then statements that are inside the always block will be executed. So we will see these three things also in this example. So let's go to Vivado and create a project. So my input is main clock. I'm taking CLK is my input, and then I'm getting different clocks like clock 2, clock 4. Okay, clock 2 is f by 2 clock, clock 4 is f by 4 clock, and I'm taking clock V1 version 1 of clock V2. We'll see what it will do. Clock V3 to demonstrate the different kind of always blocks. Okay, so initially I have to assign all these clocks to 0. So I'm assigning clock 2 is equals to 0. Similarly, clock 4 is equals to 0, and clock V2 is equals to 0. Clock V3 is equals to 0. Clock V1 is equals to 0. Okay, begin and this is the initial block. It will only execute once. That is why it is an initial block. Now I am defining always block, always at the rate pausage of clock. So what we learned, whenever there is a pausage, I want to flip the clock 2, right, to get the f by 2 clock. Clock 2 is equals to negation of clock 2, right. Similarly, if I want to get the clock 4, I need to define an integer count is equals to 0. You can define directly count is equals to 0 here, or you can define inside the initial block also. Both are same. Always at the rate pausage clock. My clock 4 begin. If my count is equals to 2, then my clock 4 should be inverted, right? And my count should be 0 because I want to start counting from 0 again. So I have to initialize count 0 here. Else simply count is equals to count plus 1. I am incrementing the count until I reach this count is equals to 2. It will increment. Once it reaches count is equals to 2, it will flip the clock 4 and it will assign again count is equals to 0, so that I will get the infinite loop. So I am ending this. Now let's see how to write both pausage and negate of clocks. Pausage clock, you can use either or you can directly write comma negate clock. So always at pausage and negate of clock, I am performing clock underscore V1 equals to inverted of clock underscore V1 CLK always at the rate pausage. Edge spelling is wrong. Okay. One more way to define is always at the rate directly CLK I can write. So whenever there is a change in CLK, the following steps will execute. Clock underscore V2 is equals to now clock underscore V2. Similarly, I will write always at the rate asterisk. I am not defining any sensitivity list. The sensitivity list is the right hand side of the following statements. Clock underscore V3 is equals to clock. I should not write clock underscore V3 because that will become the sensitivity list. I want clock to be the sensitivity list. That's why I'm writing clock. Any error? There is an error here. We haven't did use semicolon. Okay. Now it's done. Let's simulate this. Since we haven't assigned anything, it is in high impedance state. Now let's force the clock using force clock. My leading edge should be 1 and trailing edge is 0. I want a 50% duty cycle and I want a time period of 10 nanoseconds. So let's run it for 40 nanoseconds. We'll see the outputs. Now see at t is equals to 0, my clock becomes 1, right? Now my clock 2 will be flipped only at the positive edges. Here it encountered a positive edge. I already told the positive edge need not to be from 0 to 1. It can be from x comma z to 1 also. That is also considered as a positive edge. That's why from z to 1 is considered as a positive edge here. And my clock 2 is flipped from 0 to logic 1. Similarly, it has flipped here from 1 to logic 0. So it is continuing same pattern. Whenever there is a positive edge, it is flipping its data. So our clock 2 is correct. Now we will go to clock 4. So what happens when clock edge is encountering, the count is getting incremented. See, during the first clock edge, the count is incremented to 1. During the second clock edge, the count is again incremented to 2. Now once it is expecting clock edge 3, my count becomes 0, because once count is equals to 2, this line of code will execute. What is this? First it will make the counter is equals to 0 and it will flip the clock 4. So my clock 4 is getting flipped from 0 to 1. So you can see the time period of the clock 4 is exactly 4 times of the clock 1, right? So from here to here it is 4 time period, right? 2 time period plus 2 time period, it is 4 time period. You can run it for 40 more nanoseconds. You can see the clock 4 is generating as expected, right? Now let's see what is clock version 1 and version 2 and version 3 are. What do we expect from clock version and version 2 and version 3? They all should trigger at clock level, right? The clock version 1 is triggering at positive edge of clock. The clock version 1 is triggering at both positive edge and negative edge of clock, right? So it is triggering at positive edge and flipping the data at positive edge, and again it is triggering at negative edge and it is flipping the data. So it is following the same pattern as the clock. Similarly, my clock version 2 is triggering it whenever there is a change in clock. So if the clock signal is changing, my clock version 2 is also changing like this. Similarly, my clock version 3 is changing based on the clock. I haven't defined any sensitivity list here. I have defined * that will take the sensitivity lists of the right hand sides. So here clock is in the right hand side. So whenever there is a change in clock, my clock V3 is assigned to clock. So that's why clock version 1, version 2, version 3 all are same and all are equal to clock. So now we know how to create the clock divider. Now let's see, let's say I want to create a 2 seconds delay. So how to do that? I have to change the counter variable to count for 2 seconds delay. So first let's do the calculation. What should be the counter value? So this is my clock. The clock inside the jetboard is having a frequency of 100 megahertz. 100 megahertz frequency means 1 by 100 megahertz will be 10 nanoseconds. So the time period of the clock inside the jetboard is 10 nanoseconds. From this 10 nanoseconds, I want to create a 2-second delay. So how many times I need to count to get the 2-second delay? So earlier in the example of clock to clock by 4, what we did, to get the frequency of f by 4, we have counted up to 2, right? Similarly, to get the frequency of f by 8, we need to count up to 4. So let's find out what is the frequency of this. 100 megahertz is my main frequency and 2 seconds is my output frequency, right? So this is my time period, not frequency. So that frequency will be 1 by 2 is 0.5 hertz. This is my frequency, right? So if the output frequency is 1 by 4 times of f, then I need to count for 2. If the output frequency is 1 by 8 times of f, then I need to count up to 4. So we'll try to generalize this thing. So if my input frequency is 100 Hz, 100 megahertz, and my output frequency is 0.5 Hz, so I want my output frequency is 0.5 Hz. So with this, how much I need to get? What is the f by divider value? 100 mega divided by question mark is equals to 0.5 Hz, right? So the question will be 100 mega by 0.5, which is 1 by 2, 200 mega. So this is my x. So my x will be 200 mega, which is 200 comma 000 comma 000. So if you count this many times, then your clock will become 0.5 Hz. So let's change the count variable to, let's do first in milliseconds, then we'll go for seconds so that it will be easy to see in the simulation, right? So I'm changing the count to 2000. Okay. Now I'm relaunching the simulation. Force clock 1 to 0, and my time period is 10 nanoseconds. Okay. And running. I'm concentrating on clock 4. So let's run it for few microseconds. Now let's see at 21 microseconds, because it's starting at 1 microsecond, it is taking 21 microseconds. Ideally, the off period is 20 microseconds, right? That is because we have given 2000 as a count variable. So if you want in milliseconds, you need to add 3 more digits here. That will push this to 20 milliseconds. But we want how much? 2000 milliseconds. So we need to add 2 more extra zeros. Then my off time period will be 2 seconds. Similarly, my on time period will be 2 seconds. So complete time period of this will be 4 seconds, right? That is what we want. So what I'm doing, I'm writing a new project where I will try to give the 2 seconds delay to my AND gate output. So this is my synthesizable delay. Earlier we did by using hash, that is not a synthesizable delay, we have already seen. Now I am trying to create a synthesizable delay using Jetboard. So in the theory we have seen, right, to get 2 seconds of, this is not complete time period, 2 seconds of off period, right? So this 200 mega will be like it is counting off period of 2 seconds as well as on period of 2 seconds. So to get complete 4-second delay, in which 2 seconds off and 2 seconds on, we need to use 200 mega as my count limit. Okay. Similarly, in this case, 4 is used for f by 8 and 2 is used for f by 4. We are using 200 mega for f by how much? It is 0.5 Hz, not 0.5 Hz. If it is 0.5 Hz, then it should be 100 mega, right? Half of it. Let's create out, comma, in 1, comma, into, comma, clock. And now I want my own clock, clock of uh, my clock. Okay. And inputs are in 1, comma, into, comma, clock. And my output is out. Now I'm doing initial, begin. I need a integer of count, integer count, initial my count is equals to 0 as well as my clock is equals to 0, and always at the rate causage clock begin if my count is equals to 200 million, 200, 1, 2, 3, 4, 5, 6, 200 million, then again begin my clock is equals to not of my clock, and my count is equals to 0, and else count is equals to count plus 1. I'm ending the always statement. Okay. Now I want my output end operation at this clock, causage of my clock. Okay. Here I am assigning out is equals to in 1 and in 2. Define it as a register because the procedural statements will expect a register as the output. I am saving this. Let's create the XDC file. For XDC file, you have to create a schematic, and from schematic, we can create the XDC file. So these are the 4 IO ports. Clock, I need to assign it to Y9 pin, and input 1, I am assigning it to T22, which is switch 1, and output is input 2 is assigned to, okay, switch 0 is F22 and switch 1 is G22. T22 is the LED. Okay, G22 and F22, T22. Right. In the JetBoard, you can see the configuration. LED 0 is T22, switch 0 is F22, and switch 1 is G22. Okay, save this. This is my XDC. XDC means X means anything like physical or timing, and DC means design constraint. We are giving right now, we are giving only physical design constraints. These are called physical designs. Okay, because we are assigning physical pins to our design. You can give timing constraints also, but we will teach them in the HDA. Save it. Now see your XDC file whether it is created. XDC file is ready. Now do the bit file generation. I am not doing implementation and synthesis individually. I am generating the bit file that will take care of all the synthesis and implementation. By that time, I will connect my JetBoard to the laptop. Open hardware manager. Open target. Connect your device. Now let's dump the code in JetBoard. Now let's see both the inputs are 0, so the output is 0. Now if I turn on one of the inputs, still the output is 0. If I turn on both the inputs, let's count how much seconds it is taking to glow the LED. 2, 3, 4. This is what we intended, right? 2 off time period and 2 off on time period. So total 4 seconds of delay we have created. Similarly, if I turn off one of the input, then output should go from 1 to 0 after 4 seconds. 1, 2, 3, 4. Okay. So this is a synthesizable delay. In data flow modeling, we have used hash delay, which is not a synthesizable delay, but now we have created a synthesizable delay.